In this example, we're going to learn how to solve a polynomial inequality. More precisely, we're going to solve a quadratic polynomial inequality. The polynomial inequality 2x squared plus 3x minus 5 greater than or equal to 0. Okay, now before we get into the details of the solution, let's first lay out a clean strategy for solving arbitrary polynomial inequalities. So the strategy is like this. So, strategy for solving polynomial inequalities. First, we want to ensure that the inequality is of the form p of x greater than or equal to 0, or p of x less than or equal to 0, or p of x maybe greater than 0, or p of x less than 0. So we need to ensure that, so in other words, what we are really ensuring is we're ensuring that we have a 0. So we have 0. So what I really mean to say here is that our first step is to ensure that the right hand side of a polynomial inequality has a 0. Okay, so that's the first step. So how do we do that? Well, if both sides of an inequality are non-zero, we just collect all terms on one side. We transfer all terms on one side, of course, assigning them appropriate signs, and our task is done. Okay, so the second step is factor the polynomial. So to do so, we need to solve p of x equal to 0. So from this inequality, we construct an equality and solve that equality, and that's a helping object so that we can factor the polynomial. Using the factorization, split the real line into regions, intervals actually, where the polynomial does not change sign. So once we do that, we are ready to read off the final answer. So I'm going to show you how to do step 4. So that's easy. So the difficult part is step 2, factoring the polynomial. So this is difficult. This is the only difficult part. Everything else is much easier compared to step 2. Okay, so that is the strategy for solving polynomial inequalities. Okay, so once again, let's recap. The strategy is, first, ensure that the inequality is such that we have 0 on one of the two sides. Usually we put the 0 on the right hand side. Next, we factor the polynomial. Next, we split, using the factorization, we split the polynomial, we split the real line into regions where the polynomial does not change sign. And then finally, we read off the answer. Okay, now I'm going to erase this recipe. and we're going to proceed with our concrete example. We already have 0 on the right hand side, so our first real task in this problem is to factor the quadratic polynomial. Okay, so before I run you through the nitty-gritty details of factoring that quadratic, let me actually ask you to guess it if you can. You can actually quickly guess the factorization of this quadratic. So please give it a try right now. You may want to pause the video and continue the video when you're done. I'm sure you guessed it correctly. The factorization of this quadratic should be 2x plus 5 times x minus 1. So how did I guess that factorization? Here's how you can do that. So when you want to guess that factorization, what you want to do is you want to say, well, the factorization is going to be of the form x times something plus something times x times something plus something else. Now, what can be, so the product of this guy, so the product of these two question marks must be 2. So the product of these two question marks must be 2, so they must be integers, so one of them must be a 1 and the other one must be a 2, because there are no other reasonable integer divisors of 2 whose product is 2. Okay, so I know that in one of the brackets I need to have 2x, and I know that in the other bracket I need to have a single x. Okay, now what happens with the other two question marks? Well, with the other two question marks, I need to have that whatever sits in here and whatever sits in there, right? If we have here something which is p and here we have something which is q, we know that p times q must be equal to -5, right? Because when we distribute here the parentheses, we're getting the term -5. That means that p and q must be plus or minus 5 or plus or minus 1. Here there are only 4 options. So that means that what we can have is we can have 2x plus 5 times x minus 1, or we can have 2x minus 5 times x plus 1. Their signs have got to be different because their product has got to be -1. Or we could have 2x minus 1 times x plus 5, or we can have 2x plus 1 times x minus 5. So there are only 4 options for the factorization. Now, maybe none of these options work. In that case, the quadratic has no nice factorization using integers, and we have to resort to the quadratic formula. But what we can do is we can quickly in our head try all of these factorizations. We can quickly uncover the parentheses in our head and see if one of them fits 2x squared plus 3x minus 5. And if you do that, and you can do that really, really quickly, especially if you train yourself, you will indeed get the correct factorization is 2x plus 5 times x minus 1. And you can do this really fast, but what happens if you're not comfortable, if you find this procedure very too complicated? You can do something else. So if you're not comfortable with this procedure, if this looks too ambiguous or too much guesswork, here's what you can do. What you can do is you can simply set 2x squared plus 3x minus 5, so you can set that equal to 0 and solve. Now this is a quadratic equation, and how do we solve quadratic equations? Well, we have a ready-made formula. In order to solve that quadratic equation, we know that x1 and x2, the two solutions are given by the formula minus b plus or minus radical of b squared minus 4ac divided by divided by 2a. So we get negative. So we get -3 plus or minus radical of 3 squared minus 4 times 2 times -5. The whole thing divided by 2 times 2. So we get negative 3 plus or minus radical of 3 squared, that is 9. 4 times 2 is 8, times 5 is 40. Minus times minus gives me a plus. The whole thing divided by 4. So I'm getting negative 3 plus or minus radical of 49 over 4. So I'm getting negative 3 plus or minus radical of 49 is of course 7. The whole thing over 4. So I'm getting either negative 3 minus 7 over 4 or negative 3 plus 7 over 4. Now that equals negative 4, plus 4 over 4, which equals 1. So that equals 1. And this one equals negative 10 over 4, which equals negative 5 halves. So this is how you solve this quadratic equation. And now how do you write down the factorization? Well, remember, if we have ax squared plus bx plus c, that always factors as a times x minus x1 times x minus x2, right? X1 is this guy, and this guy is x2. So, if you remember, this was the pattern for an arbitrary polynomial. An arbitrary polynomial factors as the leading coefficient times x minus the first root times x minus the second root times x minus the third root, as many roots as is the degree of the polynomial. Okay, so now we have factored. So we have factored our quadratic. So the number a here is equal to 2. X is x, and x1 is equal to negative 5 halves, and x2 is equal to 1. So that is our factorization. And as you can see, this factorization that we get through this completely standard method looks quite similar to this factorization, but there is a small difference. So this term here, x minus 1, is exactly the same as that term. But this term, 2 times x minus minus 5 halves, is not entirely identical at first glance. So at first glance, you may think, well, this term here, x minus minus 5 halves, is times 2 is different from 2x plus 5. But that's really only an illusion, because see, first, if we can simplify that, first x minus minus 5 halves is x plus 5 halves. And next I can take that 2 and I can distribute it inside to get 2 times x plus 5 halves times 2. The 2 of course cancels, times x minus 1. So I'm finally getting 2x plus 5 times x minus 1, which is exactly the factorization that I'm having here. Okay. We reviewed the methods for factoring quadratic polynomials. The first method was guesswork using Vieta's formulas, or just pure guesswork. And the second method was completely standard. Just use the quadratic formula to find x1 and x2, and then factor in this way. Okay, so now we have. So I'm going to erase what I wrote by hand, and we're going to continue with our problem. So now we have. So now let's proceed. We got 2x plus 5 times x minus 1 greater than or equal to 0. So the left-hand side vanishes when x is equal to negative 5 halves, right? So the left-hand side vanishes either when 2x plus 5 is equal to 0, which means that 2x is equal to negative 5, which means that x is equal to negative 5 halves. Okay. Of course, we knew that because we remember that x equal to negative 5 halves was one of the roots of this quadratic. So the left-hand side vanishes when x is equal to negative 5 halves. So I have marked negative 5 halves on the real line there. Or the left-hand side vanishes when x is equal to 1. If you set x equal to 1, of course, this becomes 0, so the expression vanishes. So I have also marked the number 1 on the real line. Here is my real line, this is my real line. And I have marked the numbers negative 5 half, and I've marked number 1. Okay, so from the beginning we factored our quadratic, and we used the zeros of our quadratic to chop the real we mark them on the real line. Next, we use the points we indicated on the real line to split the real line, to chop the real line into intervals. In this case, into 3 intervals. Here's the first interval. The interval here, this interval. So that's the interval from negative infinity to negative 5 halves. So the interval from negative infinity to negative 5 halves, this interval. That's the first interval we're having on the real line. The next interval is the interval from negative 5 halves to 1, this interval here. Okay, this interval. And the final third interval we have is this one, the interval from 1 to infinity. So we have our 3 intervals. I claim that my polynomial does not change signs as the value of x moves inside one of these intervals. So I claim that when the value of x is constrained to a single one of these intervals, the value of the quadratic does not change from positive to negative. So the value of the quadratic does not change signs. Let's think about this interval. Let's take a look at the interval from 1 to infinity, this one. And let's take an arbitrary point in there. So here's an arbitrary point x. So I'm going to imagine that the variable x moves inside this interval, so it moves here. And I'm going to think carefully about what happens with the value of the quadratic as x moves inside that interval. So let's think about it. If the value of the polynomial were to become 0 somewhere inside, so the value of the polynomial cannot become 0 anywhere inside this interval, because we already know that the polynomial can become 0 only here and there. But now, the polynomial is a continuous function. So it cannot jump from positive to negative without first becoming 0. So that implies that my polynomial is either entirely positive here or entirely negative, one of the two. So my polynomial is either entirely positive or entirely negative. Which one is it? Well, let's think about it. If I pick an x inside that interval, I know that I can get only one possible sign. So let's pick a gigantic x. So let's pick x equal to 10 billion. Okay? So we're picking a gigantic x. And of course, when we pick a gigantic x, that term here, if x is equal to, okay, let's say 1,000,000. So if x is equal to 1,000,000, this term here, let's not even bother computing it. We know it's going to be positive. So we know that this term here is going to be positive. Right? This term here is going to be positive. And when x is 1,000,000, well, then x minus 1, it's still huge. Okay? So this term here continues being positive. So when x is between 1 and infinity, this term here continues being positive. Right? So this term is positive and that term is positive. So what I want you to do when faced with such problems is I want you to actually mark the signs of the terms that compose your polynomial, but rather than computing actual values, I want you to either write a plus or a minus if you know whether a given term is whether a given factor of the polynomial is positive or negative. Okay, so let's see what's going on. What's the final sign of my quadratic when x is inside this interval? Well, since it's the product of two positive things, the final sign must be positive. So inside that interval, my polynomial is positive. Okay, now let's consider the next interval, the interval from negative 5 halves. Let's consider the interval from negative 5 halves to 1, this interval here. Okay, we're considering this interval. Now, what happens with this expression here, 2x plus 5? Well, 2x plus 5 let's think about it. X is bigger than negative 5/2, right? So I know that this term here is either entirely positive or entirely negative within that interval, which means that I can just pick an arbitrary sampling point. Say I can pick x equal to 0, and if I replace x with 0, so if I set x equal to 0, 2x plus 5 becomes 2 times 0 plus 5, which is 5, which is positive. So I know that this term here, 2x plus 5, this term is positive. So this term is positive. So I know that that term is positive when x sits inside this interval, right? I know that when x is equal to 0, the term is positive, and I know that it cannot change sign, so if at one place it's positive, then everywhere within that interval it must be positive. Okay. What about the term x minus 1? Well, again, we can set x equal to 0, and if we set x equal to 0, x minus 1 is now equal to 0 minus 1, which is negative 1, which is definitely negative. So this term here is negative. So that term is negative when x is between negative 5/2 and 1. So now, inside that interval, we're having the product of something positive times something negative. So the final sign is negative. So my entire quadratic is negative when x is between negative 5/2 and 1. Finally, what happens inside this interval from negative infinity to negative 5/2? Well, if we pick x to be tremendously negative, so if we pick x equal to minus 1,000, this term here, well, if you replace x with negative 1,000, that term is clearly negative. It's negative 2,000 plus some small number, so it's clearly negative. And again, if you pick x equal to negative 1,000, well, if you then this guy becomes, well, negative 1,000 minus 1, so negative 1,000 minus some small number. So altogether, this term is negative as well. So when x is very, very negative, this term is negative, and this term is negative as well. So when x is inside the interval from negative infinity to 5/2, so when x is inside that interval, my quadratic must be altogether positive, because it's the product of two negative quantities, right? So when you take a negative quantity and you multiply by another negative quantity, you get a positive quantity. So we figured it out. Our function f, so if this is our function f is positive in that interval, negative in that interval, and again positive in that interval. Okay? So we figured it out, and our problem is essentially complete. Yes, once again, if you're having difficulty figuring out the signs of your quadratic inside each of these intervals, what you can always do is select a sampling point. So select an arbitrary point, say minus 100. You can select one point inside that interval. You can select one point inside this interval, here 0, and you can select one point inside that interval, and just use that point to test. You test the value of f inside that interval, test the value of f on the point inside that interval, test the value of f on the point inside that interval, and what you get determines the sign of your quadratic. Okay? So that's what you can do. And we're essentially done. Our final answer is that x must belong, so we're asked that this quadratic be positive. So that means that x must belong to either this interval or x must belong to this interval. So x must belong to the interval from negative infinity to negative 5/2, union with the interval from 1 to infinity. Now you may want to So what happens when I plot this function? Well, I'm getting exactly what you would expect. I'm getting something positive here, and something negative there. Now, one more detail, one final detail. Why do I have here a bracket rather than a parenthesis? So why did I use a semi-closed interval? Well, because we have a strict inequality. So the recipe goes like this. So use brackets. So use brackets when the inequality is non-strict. So this is a non-strict inequality. So it has an inequality together with an equality sign. So that is a non-strict inequality. So then we use a bracket. If the inequality is strict, so it's greater than or less than inequality, then we use open parentheses. Okay, our problem is solved.